Hi, my name is Mark Bright, and in this video presentation, I'll be providing a review of a research paper called Overcoming an Untrusted Computing Base, Detecting and Removing Malicious Hardware Automatically. I'll be providing an overview of the purpose of the paper, as well as the background knowledge needed to understand the concepts and topics presented within the paper. I'll be reviewing the process that the paper follows in its approach to the problem that it identifies, as well as the results and conclusions of the approach. The general layout of my presentation is as follows. I'll start by describing and explaining some of the background topics and knowledge that you need in order to understand the paper at a basic level. I'll then describe and go into the problem that the paper seeks to address, and that'll lead to my summary of the paper. I will explain the approach that the authors of the paper take to addressing the problem and their solution that they ultimately come up with. I'll describe the validity and the efficacy of this solution, and then conclude with the key takeaway and the final remarks that you should draw from this video presentation. In order to understand the discussion that the paper provides, a common knowledge and a basic understanding of electrical circuitry is needed. An electrical circuit is any physical or theoretical network that takes a set of input signals and manipulates them somehow to result in a set of output signals. The two types of circuits in the digital world and in electronic circuit boards are analog and digital. Analog signals are typically voltage varying signals, and they're not strictly one level or another. They can be a wide range of voltage levels from 0 volts to very high levels of voltage depending on the nature of the circuit. And the other type of circuitry is digital, and digital circuitry often works in ones and zeros, which in terms of voltage can translate to 5 volts, 12 volts, or whatever other voltage threshold is specified by the circuitry designer. For the purposes of this discussion, and with relevance to the paper being reviewed, the type of circuit that we're going to focus on is digital circuits. Digital circuits make heavy use of logical building blocks, as shown on the slide now. These 8 logical blocks are referred to as gates. Going row by row, starting with the top left, we have buffer, inverter, also called a NOT, an AND, a NOT AND, an OR, a NOT OR, an exclusive OR, and an exclusive NOT OR. The NOT AND at the top right is simply an AND logical block with an inverter following it. The inversion of a logical signal from true to false or false to true is denoted by the small circle at the right of the logical symbol. So the inverter, which is a triangle flipped 90 degrees to the right, has a small circle at its tip. The NAND also has this small circle, as does the NOT OR, as does the exclusive NOT OR. The shape of these symbols and what they represent has been standardized across the electrical engineering industry. Here are the truth tables for 7 of the logical blocks presented. From left to right we have the NOT logical block, we have AND, NOT AND, OR, NOT OR, exclusive OR, and exclusive NOT OR. The bottommost row is the truth table that describes the relationship between the output and the input of the logical block. So for the NOT, we have a simple case of where when the input is 0, the output is 1, and when the input is 1, the output is 0. For the AND, both input signals are required to be 1 in order for the logical unit to output a 1. This is inverted with the logical NOT AND, where whenever the circuits are both not 1, the resulting output is 1. For the OR, only one of the signals has to be 1 in order for the output to be 1. For the NOT OR, neither of the signal can be 1 in order for the output to be 1. The exclusive OR only wants a single input to be 1. If both inputs are 0 or both inputs are 1, then the output is 0. Otherwise, when one of the inputs is 1 and the other is in an opposite state, the output is 1. The exclusive NOT OR requires both outputs to be the same value, either 0, 0 or 1, 1, in order for the output to be 1. The logical gates presented here, as well as their truth tables, constitutes the basic logical implementation within digital circuitry. So why are these gates important? Well, the gates presented here form the backbone of advanced logical behavior implemented by complex digital circuits found and used across many digital devices nowadays, such as your smartphone and your digital computer. You can arrange these gates into sequences or combine them into groups to implement very advanced logical behavior. Here are a few examples. When you start combining these logical blocks and joining them either in series or in parallel into larger groups, you get schematics that look like the following. On the top left, we have a basic AND logical block with a NOT OR in parallel and their inputs feeding into an OR. This resulting OR logical block is in parallel with another AND block, and their outputs together constitute the output. Below that circuit on the bottom left, we have the circuitry for a basic logical flip-flop. Also referred to as a latch, these circuits are capable of storing the value, either high or low, for a certain amount of time. If you ever heard of the term volatile memory, this is what volatile memory looks like at the schematic level. When the circuit loses power, the information stored in this flip-flop or latch is lost, and it's not persistent. But it can store a bit, either a 1 or a 0, so that programs running in a microprocessor or a more complicated logical circuit can pull information and store information to a register or a series of flip-flops during the execution of the program. The circuit to the right is a little bit different and looks slightly different from the circuits on the left. In the real world, the basic logical blocks of AND, OR, and all the others are formed by combining what's known as MOSFETs. MOSFETs stand for metal oxide silicon field effect transistors. In other words, they're like the valves in a water system, but for electrons and electricity. You can have a gate on a MOSFET with a source and a sink, and by activating or energizing the gate with a current, you can allow current to flow from the source to the sink in the MOSFET. Combining these MOSFETs into certain arrangements and configurations allows hardware designers at the basic physical level to implement the basic logical gates on the left side, and as shown in the previous slides. It can take a very large number of MOSFETs to implement the logical blocks shown on the left, and as discussed before, as well as the gates and latches mentioned. Here are two physical examples of complex logical circuits implemented in the real world. On the right, we have a board that's used for information processing from a remote camera through Wi-Fi, and on the board you see several black squares. These black squares are integrated circuits, and they're usually how most logical circuits come pre-packaged such that you can install them into your existing circuit. These integrated circuits can often have thousands, if not tens of thousands, of logical blocks or transistors within them on a die. The inputs and outputs of the integrated circuit are the pins found at the edges of the packaging. So on the very right side at the bottom, we have two integrated circuits with 8 pins total, and any number of those pins could be inputs and the remainder of the pins could be outputs. At the bottom center of that board, we have a much more complex IC with many more pins. On the left side, we have a microscope image of the circuitry of a digital modern processor. It becomes apparent that it's virtually impossible to actually make out any of the individual logical circuits within this die. Modern processors can have so many logical elements and transistors that when actually looking at them physically, there is no distinguishment between the individual circuits themselves. It's just one conglomerate of transistors and logical elements. So due to the sheer number of logical blocks and transistors required to implement the advanced logical behavior that's provided by microprocessors, you have to use some very powerful tools in order to be able to design such hardware. And that's where we're at now. We use software mainly to design PCBs and complex circuits as shown on the right, and especially to design the high-density transistor dies shown on the left found in most common processors. Here's what that software looks like. There's two ways to design digital circuitry. You can do it visually or you can do it through code. On the left, we have a common software suite called Multisim, and it provides a visual way to design circuit schematics. Within the circuit schematic example, we have a couple of IC packages, the 4 blue squares that are shown, along with the voltage input, a logical NAND at the bottom, and a hexadecimal display output. On the right, we have an example code for the Verilog hardware description language, and this hardware description language provides electrical engineers and digital computer engineers a means to actually design circuitry through code alone. So in terms of implementing complex logical behaviors, designers often will resort to these two methods and primary means, not necessarily specific to Multisim or Verilog, but in terms of visual schematic design programs and hardware description language compiler programs to design complex logical circuits. Now this provides a certain level of abstraction to such designers from the system, the resulting logical circuit. And so we have to ask ourselves what problems can arise from this abstraction. Could this amount of abstraction provide a means and an avenue for us to miss something that may end up being a design flaw, or even worse, an attack vector for a threat actor or a malicious system designer that wants to incorporate a means to attack the circuit later on? The answer to that hypothetical question is yes. Attackers and threat actors can, during the design process, insert hardware maliciously into the circuit that may otherwise go unnoticed by other system designers due to the level of hardware abstraction that the software tools and pipeline provide. Here's an example. On the left side, we have a basic logical schematic and a circuit, and on the right side, we have a maliciously inserted AND gate that changes the output behavior of the circuit. Now, depending on the test case inputs that the system designers use to verify the correct logical operation of the circuit prior to deploying and fabricating it in hardware, the set of test inputs that may be used to verify the correct operation of the circuit may not actually activate the malicious section of the circuit. So in other words, the malicious behavior is designed only to occur outside of normal test conditions, and the malicious behavior will not be recognized by the system designers because their test case do not cover the set of circumstances in which the malicious actor inserted hardware would activate. So this mechanism of attack on the hardware circuitry can be uniquely triggered. And like I said earlier, the complexity of circuits and the source code can obscure the inserted code or inserted schematic sections such that other system designers don't pick up on it, and they don't recognize the malicious circuit during design and testing verification, since the test cases don't encompass the set of conditions used to activate the section corresponding to malicious activity. The paper that I'm reviewing discusses a strategy called Blue Chip. Blue Chip is their approach for using hardware and software to identify malicious hardware that's introduced into the circuit and circuit design by a threat actor. The basic idea is this. Blue Chip will use an algorithm to scan all of the code and all of the signals flowing within a logical circuit to identify any sections of the circuit that are not used under the normal test cases. In other words, it will look for any circuitry that doesn't have an effect on the output when considering the normal set of inputs that the system can be expected to receive. The Blue Chip algorithm, when it identifies any unused circuits, also called unused circuit identification or UCI, the Blue Chip algorithm will introduce its own hardware with a link to software that executes in parallel, and this hardware, when activated, will raise an exception that the software can recognize. So what makes a section of hardware malicious? Well, ultimately, it's any section of hardware that does not have an effect on the output given the normal expected test inputs that is used during design verification. It's important to note that just because the section of circuitry does not affect the output during the test inputs, that the section of circuitry is malicious. So Blue Chip, while being aggressive in its approach to finding potentially malicious sections of hardware, also provides a means to allow proper operation of the circuit during design testing and verification. When scanning the hardware description source code for malicious logic, like I said earlier, any section of code that doesn't affect the output during the test cases is considered malicious. Now, not every code that gets flagged as malicious actually is malicious. This approach to scanning and flagging sections of code is called code coverage, and it's essentially looking at how much code is there and what portion of the code don't ever get executed when validating the circuitry against the test inputs that are expected. The algorithm employed by Blue Chip constructs a data flow graph from the hardware description language source code as well as any schematics employed, and a list of signal pairs is generated. Then, we iterate through this graph and the signal pairs to identify sections of code that don't have an effect on the output of the circuit given the set of test inputs. Here's an example. I would like to point out that the schematic in the top left is recreated from an example figure presented within the paper. If you'd like to see a higher level discussion about this example attack circuitry introduced by a threat actor, you should go read the paper yourself. But in other words, what you see here is 3 multiplexers. A multiplexer is a logical device that allows switching between 2 inputs based on what value the signal is. So on the top left and the right side blocks, we have 2 multiplexers that both have a control input of control 0. Now, depending on the value of the control input, the multiplexer will switch from either 0 or 1 and allow the signal corresponding to 0 or 1 to flow through its output. So in the top left, an example would be if the control input pin is 1, so control 0 is 1, then the threat value will pass through via signal input 1 and go out to A. If the control 0 signal input is 0, then the safe signal through input pin 0 will flow in and go out to the output pin A. This specific circuit is designed so that if control 0 and control 1 are the input signals for the circuit, the input set 0, 0, 0, 1, and 1, 0 will allow a safe signal to pass through all the multiplexers to the output of the overall logical circuit group, with a value of 1, 1 being the value of inputs that the threat actor would like to feed into the multiplexer and the overall logical circuit group in order to allow a threat value to pass to the output. So in the paper, an example is provided of how the blue chip algorithm uses graph theory to identify signals and signal pairs that end up not really having an effect on the output during the normal test cases. I'll show you an example now. Before I switch slides, observe the pathing of the signals from the safe and threat blocks to A and B and to the output. I'll give you a few moments to do so. Let's consider the test input of 0, 0. So in this case, control 0 is 0, and control 1 is also 0. But due to how the multiplexers in the test logical circuit are arranged, the bottom left multiplexer doesn't have any effect on the output of the circuit, since the right side multiplexer is selected to 0. So since the right side multiplexer is selected to 0, it's going to output whatever value is provided from A, and whatever value goes to A depends on the value outputted by the top left multiplexer, which is also switched to 0. So in this case, a safe signal is being sent to the output. Now the blue chip algorithm, in its generation of pathing in the graph and signal pairs, will eliminate the signal pair between threat and A, threat and B, and threat and out. So in this slide, these signal pairs and the pathing from threat to A, threat to B, and threat to out have been removed. Let's now consider the test case of 0, 1. Now, although we switched the bottom left multiplexer's input from 0 to 1 so that it's now passing the threat value to B, we didn't change the first bit or the value for control 0. So the multiplexer on the top left is still feeding a safe value to A, and the multiplexer on the top right is still feeding A to out. The blue chip algorithm in this case will simply remove the path link between safe and B and out. So now we're left with just the signal pair path between safe and A and out, and safe and out. We now consider the test case of 1, 0 as an input. Now the output of the circuit here is the same, it's still safe, but the signal flow is different. The top left multiplexer is no longer feeding a signal being used by the right side multiplexer, since the right side multiplexer has an input control signal of 1, so it's drawing its value from B. Now the bottom left multiplexer is using the second input of 0, the control 1 input, to select 0, so it's feeding a safe value to B. So although the right side multiplexer is now using a value provided by a different multiplexer, the net result is that the output of the circuit is still the safe input value, regardless of whether the input came from the top multiplexer or the bottom multiplexer, and for at least test cases 0, 0, 0, 1, and 1, 0. So in the end, the blue chip algorithm and its use of graph theory has eliminated the threat circuitry, the circuitry handling the value of B, and the circuitry handling the value of A, and has made the determination that through the 3 test cases, only one signal pair is remaining, and that's between safe and out. And so all the circuitry that's described in the top left can be considered malicious, because it doesn't really have an effect on the output given the set of test inputs used during the design, verification, and testing phase. Now after scanning the circuit design HDL source code for a malicious circuit and identifying one, what does blue chip do? Well, it uses a signal pair from the process I just described to define a source and a sink. So the input safe that was described in the previous graph is defined as the source, and the output, called out, defined in the previous graph, is defined as the sink. Blue Chip will then replace the hardware section that it deemed as malicious with its own hardware. This special hardware will store copies of the sync, or the out signal that I just used in my previous example, such that if the circuitry goes into a state that's not covered by design and verification testing, Blue Chip will then copy its locally stored backup of the sync value and use that instead. This approach will effectively prevent against hardware attacks where the threat actor has inserted malicious hardware and hopes to use a specific set of inputs to activate the hardware such that it can feed a malicious output signal to the output of the overall logical system. So now that we know how Blue Chip works and how it can protect against attack, what makes this technique special? Well, the primary advantage of Blue Chip is that it replaces malicious hardware sections with its own within the HDL code. Doing this in conjunction with the execution of software in parallel allows Blue Chip to permit the system to recover from a hardware attack and resume normal operation. In the paper, 3 attack types such as privilege escalation, memory redirection, and shadow mode are tested against Blue Chip. Blue Chip successfully prevented all 3 attacks, but was only able to recover from 2, which may be a potential downside for some system designers. In addition, the technique employed by Blue Chip introduces some system overhead. Now the overhead isn't that much, it's only 5%, but this may not be suitable for some systems depending on what their timing requirements are. For safety critical systems as well as real-time systems, Blue Chip may not be suitable because of some spurious behavior from the way that it intercepts hardware attacks and recovers the system. So what are the key takeaways from this video presentation? Well, we saw and explained how Blue Chip works and how it provides an automated way to identify malicious hardware within very large logical circuits. Blue Chip offers the unique advantage of being able to recover from hardware attacks, and although it has minimal overhead, it may not be necessarily suitable for systems that are safety critical or have real-time requirements. All images used were either made by me, taken inside my electronics laboratory, licensed under Creative Commons, or are referenced from either of the references below. Feel free to go read the paper for yourself to get a further understanding of the principal operation of Blue Chip as well as its results. I hope this video presentation helped you and garnered your interest into the paper.